Okay, welcome to the next Flipped Classroom class activity. Today we're going to be talking about vectors, arrays, and matrices. So this is class session 8 in the EECS 1011 class at York University. Okay, so the thing to remember about the Flipped Classroom is that it's important to review all of the class material ahead of time. That includes videos, book sections, this slide deck, etc. The idea is that after doing so, you'll be ready to come to class and do active learning in class. We're going to be doing group activities, discussions, exercises. We'll be using the Scantron bubble sheets, for instance. And so all of that is made possible by you having a look at this information ahead of time. In terms of the book chapters that you should be looking at, here specifically we want to highlight sections 1.6 and 5.2 of the Attaway book. So that's chapter 1 and chapter 5, sections 1.6 and 5.2. And effectively what we're looking at are vectors and matrices and operations on vectors and matrices. Now, today when we're talking about vectors and matrices and arrays and scalars and things like that, effectively what we're talking about is something that you're probably already familiar with. You've probably already used Excel. It's a spreadsheet program, and you've probably in Excel already organized data in horizontal rows and vertical columns. So effectively, you've probably done something along these lines where you've drawn or written information in rows like here. Okay, so here's a row right here. That's one row of data. Or in column format. Okay. So you've probably done something like this in Excel before. MATLAB does something very similar, and so we'll talk about that today. So in MATLAB, we arrange data in rows and columns, and we typically call these things arrays or matrices. And I'll talk about the distinctions between scalars and vectors and arrays and matrices as we go along. So an array is effectively a multi-dimensional table. Okay, so in Excel what you've got is a two-dimensional table typically, rows and columns, rows being one dimension and columns being another dimension. And arrays can be one-dimensional, two-dimensional, or three-dimensional, etc. The size of the array, k, which could be 1, 2, 3, or maybe even 4, for instance, is specified by D1, the number of rows, D2, the number of columns, etc. So D1 would be the number of rows, D2 is the number of columns, and if you have a one-dimensional array where all you have is a row, you can have this, for instance. This is a one row, three column vector, or this is a 5-row, 1-column vector, or you can have an array of 4 rows and 2 columns, or you can have a 3-dimensional one where you have 2 rows, 1 and 2, 3 columns, 1, 2, and 3, and then you can have 5 sets of these in depth, and so that would be a 3-dimensional one. And then over here, the one we didn't talk about earlier is something called a scalar, and effectively it's just a single number. So there are many ways to create arrays, and they can be of all sorts of different sizes, and sometimes you need to determine what the size of an array is. And so the best command to use for that, for determining that sort of thing, is something called size. So if you wanted to determine, for instance, the size of a particular arbitrary variable, you would say size, open parenthesis, my variable, close parenthesis, and hit enter. It's possible to have a variable of size or an array of size 0, so nothing in it, or it's empty. And so if you want to create an empty array, so my empty array is equal to open square bracket and close square bracket, you'll actually have an array of nothing. And if you try and type in size with square brackets like this, you'll see that it gives you the answer of effectively nothing in MATLAB. So a quick little summary here. Basically what we're talking about when we're talking about arrays and things like that in MATLAB, we're talking about things like scalars, which are effectively single numbers. You have arrays, which are sets of numbers 1 or more. You have vectors, which are one-dimensional arrays, so a set of numbers that fits into either a column or a row. And then you also have matrices, which are arrays that typically we think of having more than 2 rows and 2 columns. And what's really interesting about matrices is that you can make them really, really big, and they can be 3-dimensional, etc. So a scalar in MATLAB is an array of size 1 by 1. So effectively, it's just a single number. Okay, so it's a single number. A vector is a 2-dimensional array where one of the dimensions is 1. So we can have a row vector, so a horizontal vector, or a vertical column vector. So in the case of the row vector, it would be 1 by 3, or 1 by 5, or 1 by 22, etc. And a column vector would be 5 by 1, or 6 by 1, or 342 by 1. You can create a row vector by saying, or putting in a command something like this: v is equal to square brackets 1, 2, 3, 4, close the square bracket and hit enter. And effectively what you'll have here is a vector that has 4 values in it, and it's ranged horizontally. You could also do it by putting commas instead of spaces. So you could say v is equal to 1, 2, 3, 4, and you'll get the same answer. You can also have the creation of row vectors by doing something a little bit different, by using the colon operator right here. And what effectively you're saying here is that you want a row vector that begins at 1 and ends with a value of 4. Hit enter and you get v is equal to 1, 2, 3, 4. So it's effectively the same thing as before. If you want to change the incrementation between numbers in that vector, you can specify the spacing or steps or increments. So the increments right here. In the setting up of your vector. So here what we're saying is that we want the vector to start at 1, so starting with the value of 1, and we want it to end with a value of 9, and we want to do it in steps of 2. So here you see that the vector that's created goes in steps of 2 from 1 to 3, 3 to 5, 5 to 7, and 7 to 9, effectively odd numbers. Now, you can do other things, like this, for instance. You could create a row vector where you're going from 1 to 8 in increments of 2. Try it out and see what happens. The next thing that you can do is you could try this. You could go the opposite way. You could see what happens if you start at 8 and end with 1. Will that work? Give it a shot in MATLAB. See what happens. You can specify how things start and stop and increment using variables. So here we're going to create a variable. Okay, so we have a variable, and its value is 5. That will be our start variable. Our step variable, or our incrementation, variable step is equal to 5 as well. We want to end or stop with a value of 25. And so we set up a vector. This is going to be a row vector that starts with a value of 5, ends with a value of 25, and we want to increment or go in steps of 5 as well. So you see we start at 5, we end at 25, and we jump in steps of 5. Now, we can do other funny things, and we can see if what happens when we want to, for instance, decrement instead of increment. Okay, so if we want to decrement, we're going to go downwards. So we start with a value of 25. We want to do steps of 5, but we want to go in negative steps, or we want to decrement in values of 5 or in steps of 5. We want to stop eventually at 5. So we want to start at 25, we want to end at 5, and we want to decrement in steps of 5. There we go. Same sort of setup as what we did before, but the variable values have changed. So we start at 25, we end at 5, and we go minus 5, minus 5, minus 5, minus 5. Okay, from there, what we want to do here is we want to observe that the stop value is not guaranteed to be at the end of the vector. Okay, all of the previous examples that we had started and ended really nicely and had nice increments all the way through. But we can change that as well. We can make it not quite evening out like that. Start at 25, we want to decrement in steps of 5, and we want to end at 6. What happens? Let's try it out. Same syntax as what we had before. And we can see that we start at 25. We go minus 5, minus 5, minus 5. But 6 is not a jump of minus 5, so it's not included. We can automate some of this as well with a function called linspace, and it does things a little bit differently than what we just did there. In the previous examples, we were saying what the exact increments were going to be. Sometimes you're creating programs where you can't really specify that, but you know that you want to have a certain number of increments. You just don't know what those exact increments are going to be. So linspace, if you type help linspace, you'll see linspace does something different. So in terms of linspace, what you do is you say where you want to start, where you want to end, but also this is the number of increments between start and stop. Not the actual values of the increments, but the number of increments that will happen. And so it figures out the exact number of increments 4 that can be placed in between 14 and 20. And that means that you're going to go in steps of from 14 to 16 to 18 to 20. Next, we started with row vectors, now we can do column vectors. And the basic difference between the two is that instead of just putting a space or a comma, what you do here is you put a semicolon. So semicolons, effectively what they do is they say that you want a new line. A new line Okay, so before what we were doing was creating row vectors, and now what we can do is create vertical or column vectors. And the main difference between setting up a column vector and a row vector is that in row vectors we put spaces and or commas between the individual numbers in between the square brackets. Here instead what we're doing is we're putting semicolons. So the semicolon effectively is telling me that I want to have a new line or a new row after each one of those numbers. So if I do v is equal to 1, 2, 3, and 4 and put semicolons after the 1, 2, and 3, I will get a column vector or a vertical vector like that. Another way of doing it is effectively to create a row vector and to do something called a transpose. So this single quote right here is what's referred to as the transpose operator. And what that will do is transform your row vector into a column vector. So it will calculate start, step, and stop into a row vector first, and then it will apply that transpose operator, and what you'll get is a column vector like that. Okay, so it's a transposed row vector. Now, the single quote is, like I was saying, the transpose. There's another term that can be used to describe it, which is the conjugate transpose. Don't worry about that for right now. And it's important to know that you can use either a dot single quote or just the single quote typically to engage the transpose operation. So that was one way of creating a column vector. Another way of doing it is to create a row vector like this. So we say v is equal to 1, 4, and that's going to create a row vector of values 1, 2, 3, and 4. And then what we do is we say that this new vector, w, this is going to be the column vector, is equal to our row vector v, parenthesis, and we use another colon here. That colon is different than the colon that was used before in terms of its function, but not of its form. Okay, so it's the same colon, but it's being used differently. So what ends up happening here is that our v vector, our row vector, is converted into a column vector, w, like this. Okay, so once again, it's important to note that the colon, has two different uses. The first one is here, and the second one is right there. So the function length can also be used in order to determine how many elements, or how long, effectively, the vector is. So if we take our row vector v, which has values 1, 2, 3, and 4 in it, and we put the command length in, and we say in parentheses, we want the length of v, it will say that there were 4 elements. There were 4 elements in vector v. It's important to note that when we're talking about length here, we're not talking about the Euclidean length of the vector, but rather the number of elements. The number of elements inside of the vector itself. That's what length tells us. We can determine, however, the magnitude of the vector, and when we're talking about the magnitude of the vector, we're talking about effectively something called the norm. There are many different types of norms. There's the Euclidean norm, the taxicab norm, and many other types of norms as well. MATLAB defaults to computing the Euclidean norm when we call the norm function. So if we have a row vector and the row vector has two elements in it, 1 and 1. So the first element is 1 and the second element is 1. If we type in norm v, so norm of the vector with elements 1 and 1 in it, it will calculate the Euclidean norm, and that's equal to 1.4142, which is effectively the square root of 1 squared plus 1 squared. Another really important function that you'll be using in MATLAB is something we refer to as indexing. Okay, so if you want to know what the value is of the first or second element in a vector, you need to know the index that you want to deal with. So one of the important things to know about MATLAB is that MATLAB uses a one-based indexing system, which means that it starts counting at 1. And this is normal for most people. For programmers or people who've done programming before, this is a little bit different because in programs like or programming languages like C, counting typically starts at 0. But MATLAB is more of a normal kind of programming interface and experience, and so it starts counting at 1. So the first element in a vector is 1, or index of 1. The second one has an index of 2. In order to figure out what the value is at a particular index, we end up using the parentheses. And we'll do it like this. Here's an example. So if we have a row vector, so this is a row vector that starts at 5 and it starts at -5 and ends at 3. So we have here a row vector that starts at -5 and ends at 3. We can request to have the first element inside of that vector right there, and that happens to be this one right here. Okay, and so the answer is -5. If we want the second element, which is -4, we hit enter after saying v open parenthesis 2 close parenthesis. The answer is -4. We can do something a little bit different as well. We can assign values to particular indexes or indices within your vector. So if we want to say that the third element of the vector variable v is equal to 100, we will replace whatever value was in there before with the value 100. This is the first element, that's the second element, and that's the third element. And the third element in the vector has a new value 100. The keyword end can be used to access the last element of the vector. Sometimes you don't know what the index is for the end of, say, a very long vector, and so you can use the word end. It's a keyword in order to determine what the value is at the last value of the vector. It's 3. You can perform math as well, or sort of mathematical variations on that. So if you wanted to get the second last element in the vector, you would say that you want the end element -1, and that will give us the second last value inside of the vector. Now we can get even crazier here with how we address things. So we can ask to have the first, third, and fifth elements. So the first, third, and fifth elements of a particular vector. And here you go. The first, the third, and the fifth elements. We can also replace the first, third, and fifth elements of a particular vector. So if we want to replace the first element with the value 7, so we want to replace -5 with 7, there you go. If we want to replace the third element with the value 8, so the third element is this one right here, we want to replace that one with the value 8, so that one's gone right there. So first and third elements are gone, and then we want to replace the fifth element, this one right here. We want to blow that one away, and we want to replace it with the value 9. There we go. We have replaced it with the value 9. Now you might have forgotten from earlier in the presentation, but what's important here to note is that typically when we're referring to arrays in MATLAB, we're referring to either row vectors or column vectors or matrices that are say 4 rows by 2 columns, or 3-dimensional matrices as well. So those are what we typically call arrays, and scalars are what we typically refer to as single element numbers. Now we can perform arithmetic operations on an array by a scalar. So we can take any of these arrays here and perform mathematical operations, additions, multiplications, subtractions, etc., using scalar values as well. So we can add, we can subtract, we can multiply, we can do different types of divisions, and we can apply powers to these as well. So here's an example right here. So if we have a row vector u, okay, so this is a row vector u, and it has the elements 1, 2, and 3 in it. So this is a vector right here. We want to make a new vector w, and we want to apply a scalar 2 to it. We say new vector w is equal to the scalar 2 plus the old array u. So we're effectively applying 2 and adding it to 1 to make 3. We're taking 2 and adding it to 2 to make 4, and taking 2 and applying it to 3 and making 5. So w is equal to 3, 4, 5. We can do subtraction as well. So we can take the values 1 and subtract it from 2 and get 1. We can take 2, subtract it from 2 and get 0. And we can take 3 and subtract it from 2 and get -1. We can do multiplications as well. So we can multiply 2 by 1 to get 2, 2 by 2 to get 4, and 2 by 3 to get 6. We can do divisions. So we can take u, the first element, and divide it by 2, and we get a half. We can take 2, divide it by 2, and we get 1. And we can take 3 and divide by 2 and get 1.5. We can do powers as well. So we can say 1 squared is equal to 1, 2 squared is equal to 4, and 3 squared is equal to 9. And so w is going to be a new array or a new row vector of elements 1, 4, and 9. We can perform the same sort of arithmetic operations on 2 different arrays as well. So 2 different arrays of the same size. Okay, so they have to have the same number of elements arranged in exactly the same way. So you can take 2 row vectors of 1 by 3 and do math operations on them, or you could take 2 column vectors of 5 by 1 and do the same thing, or 2 of these 3-dimensional matrices right here and do the same thing. So we can do additions, subtractions, multiplications, and you'll notice there's a little period right before the multiplication right there. You can do right array divisions. So again, there's a little period right before the division sign. Then there's a funny left array division, okay, and again, there's a decimal point or a point right there, and then powers as well, okay. So typically when you're performing math operations on 2 different arrays at the same time, you proceed the normal operator using a period. Okay, so if we have the first row vector u, and the second row vector v set up, and we want to add the two together. So we want to create a new row vector called w that is the addition of u plus v. Effectively, what will happen is you will add 1 to 7 to get 8, you will add 2 to 8 to get 10, and 3 to 9 to get 12. Okay, and that is the new row vector w. You can do subtraction as well. So if you go 1 minus 7, so u minus v, so 1 minus 7 is the first element, it's minus 6. Second element of u is 2, second element of v is 8. We subtract 8 from 2, so u minus v, and we get minus 6. If you take 9 away from 3, in the third element of u and the third element of v, you get minus 6. You can do multiplications as well. So if I want to multiply all of the elements in u against all of the elements in v, so this is an array or a matrix style multiplication, you want to go element by element. So the first element in w is going to be 1 multiplied by 7. So the first elements of u and v multiplied together. Then the second elements 2 and 8 give you the second element of w right there. And the third elements of u and v multiplied together give you 27. You can do a right array division. Okay, so that's the normal one that we typically think of. So if we're going to divide all of the elements of u divided by all of the elements of v, so all of the elements of u divided by all of the elements of v, we go 1 divided by 7, that's the first element in w, 2 divided by 8, that's the second element in w, and 3 divided by 9 is going to be the third element in the new array or new row vector w. There's also the left array division, which is effectively the opposite kind of division. So if we go u, left array division of v, what ends up happening is you go kind of the opposite direction. Okay, so it's v divided by u. So 7 divided by 1 gives you 7, 8 divided by 2 gives you 4, 9 divided by 3 gives you 3. You can do powers as well. So if you go u to the power of each element inside of v, you go first element to the fourth power, gives you 1. Second element to the second element power is 32. And third element to the third element power gives you 729. Okay, there are all sorts of other examples of operations that we can do. We can do calculation of norms, so we can do in order to get unit vectors. So if we want the unit vector of v, we do v divided by the norm of v. We can do dot products as well. So if we have two different vectors u and v, we can do dot products this way. Either sum with a matrix multiplication there, or we can use the dot operation. We can do complicated things like computing the body mass index, where m is the vector of masses in kilogram of a number of subjects, and h is their heights in meters, for instance. And here you go. Here are matrix or array divisions and multiplications and power functions. And we can do plotting of different functions as well. So we can set up a linear space from -5 to 5 in increments of 1. We can do the function y is equal to exp of -0.5, multiplied by x to the second power, divided by a scalar square root 2 pi. And that's the plot right there. And we can plot functions as well, okay, like this. And this is how we would do the plotting of this function right here. Okay. Now, what's important to know is that during the flipped classroom activity, we are going to be expecting all of you to have reviewed these slides ahead of time. You can use the free web-fast version of MATLAB to practice everything that we do here. Make sure to bring a regular graphite pencil, an HB pencil, to the class because we're going to be doing Scantrons. And this is how you fill in a Scantron properly. So this is really important to know, that your ID gets bubbled in here. You have to write it out manually as well. You have to write your name up here. You have to put the class name, the date, and rewrite your student number right there. And then you will fill in all of the values for all the different questions right there. Thank you very much.